lectures, basically almost the rest of the semester, working on the geology of South Africa. So this, as I've already explained, is one pretty important for your overall training as civil engineers, that when you go out there to work in South Africa, you need to have some appreciation of the rocks underneath that you're going to be building roads or bridges or whatever the case may be. So this map of South Africa, I hope in the course of the next 2 weeks or so will become familiar, and that you'd be able to look at this map and get some understanding from it. That if you were dropped off somewhere, you'd be like, oh yeah, this is where I am, this is the rocks that I'm in, more or less the age and what's going on with them. So we've talked about the geological timescale and the different eras of geological time that are divided up, and this map is arranged against the geological timescale. So we have the Archean, the Proterozoic, and the Phanerozoic. And then within that, we have the geology of South Africa. And this Archean record, this dark and light purple, make up a large part of this northern part of South Africa. And we have this incredible Archean record. So we're going to spend quite a lot of time looking at that. And then basically, yeah, this color code of the map, all the major color groups, is a major rock formation, a supergroup of rocks. So for example, this is the Cape supergroup down here. So yeah, we're going to keep referring to this map, and as I said, it really needs to become familiar to you that these colors all begin to mean something. So we're going to start off today and going over into tomorrow. We're going to be looking at the first 2 billion years of this geological record. So when we teach this to our geology students, we can spend weeks doing this, and we do it in first year and again in third year. But you guys are getting a kind of whistle-stop tour. So we're going to start off looking at the oldest rocks in South Africa, which are found in the Limpopo belt. Then we're going to go to the Barberton supergroup, which is around the town of Barberton, and have quite a look at these Archean rocks, where we have this incredible, it's called a greenstone belt, and we're going to use Barberton as an example to understand these ancient greenstone belts. Then we're going to look at a craton. I spoke about cratons on Tuesday, these ancient fragments of crust. We're going to look at the Kaap-Vaal craton, which underpins the basement of all of South Africa. We're going to look how this is assembled. And on top of that, we're going to look at the Witwatersrand supergroup, which contains the gold, which is why Joburg is where it is. And lastly, have a quick look at the Vetersdorp supergroup. So this is for the next 2 days. We'll just see how we go. And then we're going to Mpumalanga, and we're going to look at the Barberton supergroup. And then finally come back to Johannesburg, and where we see these red rocks outcropping its surface. These are patches of the Witwatersrand supergroup. Much of the Wits group is subsurface, which is where the gold mines are. So before, we're just going to take one step backwards and look at this early history of the Earth. So around 13.7 billion years ago, we have the Big Bang and the formation of the solar system. And then we have a long period of kind of space history, where we have stars, and in these stars you have various nuclear processes and the kind of formation of elements. And eventually, by around 4.6 billion years, we have a consolidated Earth. So the Earth is beginning to cool and consolidate, and is already segregating into a core. So we have this very hot liquid iron core, and then a mantle. So we have different, a segregated Earth. And by 4.6 billion years, the Earth has cooled enough that we have some evidence that there's at least water vapor. And then at around 4.4 billion, so I checked this and it is 4.4 billion, we have the oldest zircons, which are from that Jack Hills conglomerate in Australia. So the rocks themselves are a little bit older, but surviving in them are these tiny little zircons, which date back to 4.4 billion years. Then by around 3.9 billion years, we have the oldest record of sedimentary rocks. So that means that we have a basin, and we've got a land somewhere which has been eroded, and this material has been washed into the basin and forming sedimentary rocks. And this record is in Greenland, and it's very poorly exposed and very poorly preserved. So, but then we move on to a very important series of rocks, where we have the oldest oceanic crust, the oldest island arc. So that's where you have a subducting slab and melting material coming up and forming an island arc, which is basically a series of volcanoes which partly erupt underwater. And we have evidence that these are then eroded. And finally, this record ends with the beginning of the first microcontinents on Earth, which are kind of stuck together with granite. And this series, this ancient oceanic crust, this ocean arc, and the evidence for erosion in a sedimentary basin is all found in Barberton. So this is where the Barberton greenstone belt and the Barberton record kind of takes the world stage, that it's the best example of these incredibly old rocks and these very early Earth processes. Yes. And then looking at Archean geology. So we've left the Hadean. The Hadean is this period from 4.6 billion to 4 billion, which is this really early period of Earth where we don't have a very good rock record from. Then from 4 billion to 2.6 billion is the Archean. And during this time, the Earth is cooled and the crust is cool enough to form continents, and we begin to have geological processes that we can recognize today. But there's a number of things about this Archean world which are very different to the world today. And one is that the Earth was still much hotter than it is today. So there was a high heat flow and very high volcanic activity. And there was plate tectonics, so we have the processes we have today where the plates on the Earth's surface were moving. But because of this additional heat flow in a hotter world, the plates were moving faster than they are today. So you get what's called crustal recycling, where this material is formed and then recycled again very quickly. So today, the tectonic plates on the Earth move, the fastest ones move, at about the speed that your fingernails grow. So if you think if you didn't cut your nails for a year, they would be several centimeters long. And our fastest moving oceanic plates move at a couple of centimeters a year. So back in the Archean, the Earth was hotter and these plates moved faster. So one explanation as to why Archean rocks are very rare today is that this whole process happened faster. The plate tectonics was faster, and as rocks were formed, they were basically recycled. Another major thing is that there was no free oxygen. So our atmosphere that we breathe today is mainly nitrogen, about 80%, with just under 20% oxygen and some other gases. But during the Archean, there was no free oxygen in the atmosphere, so it was a very different Earth. But then other aspects of geology were the same. We had ocean basins, we had volcanoes, we had oceans, we had erosion, and the deposition of sedimentary rocks. And these rocks are known as greenstone belts. And the other major component of Archean geology are granites. And these granites and greenstone belts kind of go hand in hand. So just to put all of this in another context and to hear it from another voice, I've got a little video talking about Archean geology, which I hope will play.
It's like going back to another planet. The Earth back before 2.5 billion years ago is very different from the Earth we know of today. Not only is the atmosphere completely different from what we have now, even the very rocks are different. Sure, they're the same. That's the principle of uniformitarianism. We'd still expect sand grains to be weathered from rocks, moved by rivers, piled into ripples. We'd still expect volcanoes to erupt, and even rocks to metamorphose. But there are a number of rocks that are unique to the Archean, and more importantly, it's the shape of how those rocks are laid together that make the Archean a very different planet than the one we have today. We're here in southern Wyoming, south end of the Wind River Range, and what we're standing on is a large green-colored rock. This rock is called greenstone, and it's metamorphosed basalt, the same basalt on an island like Hawaii, or flowing off of the mid-ocean ridges. In fact, you can see some features in these rocks that are similar to the rocks you find in Hawaii, such as pillow basalts, places where the lava water and quench so quickly, extruding pillow structures that look like toothpaste coming out of a toothpaste. But there's other rocks here that make the Archean particularly unique. In particular, a rock called composite. Composite is similar to basalt, that it's a mafic igneous rock, meaning to a geologist it has very low amounts of silica, that binding component that holds minerals together, and lots of iron and magnesium. In fact, the composition is what we call peridotite, or what we expect to find in the mantle of the Earth today. So what's significant about composite having a peridotite composition is that's the equivalent of saying the mantle was coming out of the Earth and forming spewing volcanoes onto the surface. Well, you don't see that now. In fact, you don't see that in any rocks younger than 2.5 billion. So what was different about this ancient Archean Earth? It had more radioactivity. When those atoms break down and release their energy, they heat up the inside. They can no longer break down and release that energy. Komatiite is also known for this amazing feature known as spinifex texture, named for a kind of grass, spinifex, that when it lays out on some komatiites under the microscope, what you see are large olivine crystals, often replaced with the mineral plagioclase, that splay out the spinifex texture of komatiites. So the rocks of the Archean can be broken out into two major types, greenstone belts and granite belts. The greenstone belts are composed of basalts as well as sediments you'd expect to find around volcanoes. The granite belts are also known as TTG belts for the three main rock types you find, trondhjemite, tonalite, and granitoids. And the rocks you'd expect to see in the major granite belts of the world today. So what ended the Archean? When did we go from a planet that was so different to the planet we know of today? The answer and the onset of plate tectonics, spreading centers and subduction zones and major transform origins. In continents, there was a major episode of granitization, melting of the crust, large volumes of this very high silica granite coming up like a sort of glue, holding together these greenstone belts and gneiss belts. When we look around the hills today, surrounding the belt are large amounts of granite that have been dated at 2.6. In fact, around the world, we find this granite episode from as old as 2.8 to about 2.4 billion years ago. In any one of those areas, once the granite came in and stuck the greenstone and the gneiss belts together, you form what we call the craton, or the center part of continental crust. We're standing.
He talked about the komatiite lavas, the spinifex texture, and these pillar basalts. And then the end of the Archean, where you get this massive intrusion of granite, which sticks these little belts together to form kind of protocontinents or cratons. So these kind of steps are what we're now going to zoom back into the South African record and look at. So just, I guess, because it's good to know, the oldest rocks in South Africa are exposed in the Sand River in the Limpopo belt on the border with Zim. And it's a granodiorite, so this is a metamorphosed granite. And you can see it's kind of the rocks that are in the background, and they've been cut through by a whole lot of much more recent dikes. We know from our cross-cutting relationships that these are younger rocks. So the older rocks in the picture are the kind of, you can see it's been, it appears layered, and this is just from the metamorphism that's kind of stretched and squashed this rock. And zircons from this granodiorite have been dated to 3.6 billion years. So that's the oldest example of rocks in South Africa. So moving on to this Barberton mountain land, to your South African map, but the pinks are still the same. So we've got, there's the town of Barberton, and this, in the greens and reds is the Barberton supergroup. And there's three major groups that make up a supergroup. We have the Onverwacht group, the Fig Tree group, and the Moody's group. So the Onverwacht is in green, which is the oldest, then the Fig Tree and the Moody's. And these collectively is a pack of volcanic and sedimentary rocks that make up a greenstone belt. And then surrounding them are these massive granite plutons. So all of the pink, we've got two different types of granite, but we've got these series of granites that make up the big hills in the area, and these are the granites which the guy in the video was talking about. It's this massive global intrusion of these granites that stick together these greenstone belts towards the end of the Archean to form these cratons. So this is just a slide saying what I've said. There's this layered sequence of volcanic and sedimentary rocks. They have a greenish color, and they're all folded because they're very ancient rocks, and they're known as greenstone belts. And this is just a summary again of the stratigraphy. So we have the Onverwacht group, which has a lower and an upper part, the Fig Tree and the Moody's. And in this Onverwacht group, we have the komatiites, this ancient oceanic crust, which we're going to look at in more detail. Yeah, and towards the top of the sequence we have more sedimentary rocks. Alright, so here we're looking at the Onverwacht group. So this is where we find these rocks called komatiites. So the type locality is the Komati River in South Africa. So where the guy in the video is in the US and talking about rocks in Wyoming, komatiites are named after the Komati River, so it's something which we can be quite proud of in South Africa, that the type locality is here. And this is what komatiites look like. So this is in the field, and this very specific texture is called spinifex, and spinifex is a type of grass in Australia that looks remarkably like this. And this spinifex texture is from rapid cooling, that these lavas have extruded at surface and then been cooled very quickly, kind of shock cooled. And they have these very typical, this is again a hand specimen, there's a finger, and this is under the microscope where we have these blades of olivine. So this is an ultramafic volcanic rock. As he said, it has very high magnesium levels and quite low silica compared to lavas today. And by doing experiments today of rocks using similar compositions, geologists have worked out that the melting point of this rock is about 1,600 degrees. So this is very hot. Lavas typically, say in Hawaii, where we have basaltic lavas been kind of erupting at surface today, they're much cooler at only 1,200 degrees. So these, between 400 and 500 degrees hotter. So there was something very different about these lavas, and it's something that's quite special that's making them hot, and it's also creating the special texture which we only see in komatiites, because they were hotter lavas which then cooled very quickly at the surface. And this is all to do with what the Archean Earth looked like and the structure of the mantle. So the mantle is this part of the Earth. This is just a cross-section through a modern Earth where we've got a crust, and the crust of the Earth is about as thick as the skin on an apple. If you cut an apple in half and you can see the green or red skin of the apple, that's relatively how thick the crust is. And then we have these various layers. We have a core in the center, an inner core and an outer core, and then what's between the core and the crust is known as the mantle. So during the Archean, the mantle was hotter, and this is because of the radioactivity of elements like uranium and potassium in the core that were undergoing radioactive decay and basically releasing all of this energy. And so we had a hotter mantle, and it's very rare today that we see rocks from the mantle at surface. And we know what these type of rocks are. Typically they're geridiatites, dunites, and eclogites. And so what's happening in the Archean is that we have a hotter mantle and a thinner crust, and there's less crust. So we're getting these mantle-type lavas extruding at surface. So this is it's quite unique to the Archean time. And that's how we produce komatiites. Would be a hot spring. But what's happening here is you've got actual molten rock, actual molten lava coming up at surface. And I had looked for some videos of this in Hawaii, where you do get video footage of molten rock at surface, but the quality is all very bad because the water visibility becomes very poor with molten rock pouring out in it. So I struggle to find some. But yeah, so it's like an extreme version. Basically, you have molten rock at surface, and it's coming out. It's because it's underwater. So I guess the deal with these pillow basalts in Barberton is that they're incredibly old, 3.5 billion years old. And what we know from finding these pillow structures is that we have volcanoes with lava coming up that's underwater. And then another rock type which we find further up in the Onverwacht group are stromatolites. So this is a type of sedimentary rock, which the oldest examples in the world really are found in this Barberton group, and they are formed by cyanobacteria. So these are small algae, blue-green algae, and they form these enormous colonies, and they make enormous microbial mats. Here's a kind of an image of a modern one, and these algae form enormous colonies and these enormous microbial mats where they photosynthesize, and the byproduct of their photosynthesis is oxygen. And so the earliest evidence for life on Earth are these cyanobacteria, and it's very rare to find fossils of tiny little bacteria, but we can find their fossil traces in these stromatolites which we find in Barberton. So there are some probable older ones in Australia, but the ones in Barberton are around 3.2 billion years old. And this is an example of a geological example where today we just see the layers from these mats of bacteria. So and they're very rare today to find these colonies of cyanobacteria. And Shark Bay in Australia is a place where we do find modern ones. So this is a photo of one of the pools in Australia where you get these modern stromatolites growing. And just to explain a bit more and give you a bit of a visual, we've got another video.
The oldest thing you've ever seen. Pyramids that are a dinosaur that is 230 million years old. How about a stromatolite fossil that is 3.7 billion years old? What is a stromatolite? Stromatolites are layered rock-like structures made by the activities of microbes. To see living examples of the world's most ancient ecosystem, look no further than Shark Bay in Western Australia. Why should you care about stromatolites? Well, one of the most prevalent microbes in living stromatolites are cyanobacteria. Cyanobacteria are microbes that feed off the sun using a metabolism called photosynthesis, just like plants. One of the most important characteristics of cyanobacteria is they provide much of the oxygen we breathe. Because of these cyanobacteria, stromatolites have played an important role oxygen-rich atmosphere we have today. Grow towards the sun, just as plants do. When you see the insides of a stromatolite, there can be thousands of individual layers, each layer building on top of the other. The newest, youngest layer is with the microbes searching for the sun. So what are we going to do if these amazing stromatolite ecosystems ever die out? It's an important stromatolites are highly susceptible to climate change and rising sea levels. Not only do these amazing ecosystems help generate the oxygen, but also living stromatolites represent an important window into the ancient Earth. Studying stromatolites helps us understand how life has adapted to changing Earth. Knowing more about guide us to understand.
So this is what we see in Barberton today. So this is how we understand, this is kind of that setting, but this is a cross-section of what we see today in Barberton. So the surroundings, we have all of these granites, and you can see the granites have been intruded and they form these hills around the greenstone belt. And then this is we've got the Onverwacht, the Fig Tree and the Moody's groups, which have been folded. So they would have originally been a horizontal series of sediments, but this whole greenstone belt has been squashed and folded by the granites and other processes. So you can see they're very folded up today. And here in this Onverwacht group, that's where we see the pillow basalts. So and then if we zoom out of Barberton and look at the rest of South Africa around this time period of around 2.6 billion years as we're coming to the end of the Archean. So we've got, we're over here, we've got this Barberton greenstone belt, and it's not the only greenstone belt in South Africa. We have a number of other ones. So on this map here, this green is the greenstone Valia, and there's a number of other small greenstone belts kind of dotted around South Africa. And then we have this major time of granitization where all these granites basically intrude up, which sticks together these pieces of greenstone belt. And what we form is known the Karpval craton. So this craton is basically the middle part, the core of a continent. And this is the beginning of the formation of the South African continent. And this Karpval craton, which consists mainly of granites, and these patches of greenstone belt. And this is basically the center of the geology of South Africa, and everything we're going to look at from now on is kind of being stuck onto this craton. So if you remember one thing from all of my lectures, the basement rocks of South Africa, the basement geology of the bulk of South Africa is the Karpal craton, which is this ancient Archean lump, basically, of granites with these small greenstone belts. Okay, so then we've had a look at these really ancient rocks and formed this Karpal craton. And then everything that happens from here onwards in the geology of South Africa, moving through time, is related to what's going on the Karpal craton. So the Witwatersrand supergroup dates from around 3 billion to around 2.7 billion years. And these sedimentary rocks, that's a giant inland sea, which would have been around where Johannesburg is today. And this is the world's largest gold deposit. Where we left off, we've just formed a craton. So the top image, we've got this pink, which is the continental crust of our craton. And what happens as we move through these images is we begin to have rifting. So we've got plate tectonics and other processes which are beginning to rift this craton apart. Just enough that it begins to basically break up on the surface, and you have an inland sea, a sedimentary basin forming in the rifts created onto the craton. And we have, go through, this is a sort of a series of models as to how we end up with this enormous inland sea, which was the Witwatersrand Basin. So this is that picture again, looking at, so we've got the outline of modern South Africa. This is our Karpal craton, and this outline here, and there's various patches here, is the extent of what's left of this Witwatersrand Basin. So not all of these rocks outcrop at surface. A lot of it is underground because it's been buried by younger material. But it's still a pretty substantially, so here's Johannesburg, and this is reaching down towards Kimberley. So it's a large, extensive basin, which was on this craton basically was rifted apart in this giant inland sea, and into this deposited the Witwatersrand supergroup. So it's a really world-famous gold deposit. So 40% of all of the gold mined in all of antiquity, so all the gold found on Earth ever is from the Witwatersrand supergroup. So the stack of rocks is about 7 kilometers thick, and it's estimated that the total amount of gold in this is about 1.5 billion ounces, so 40,000 tons of gold. And we're looking at a time of around 260 million years of deposition. So this basin was there for an incredibly long time, and it's characterized by mainly sedimentary rocks. So we have sandstones and conglomerates. We're going to talk more about conglomerates. But the gold-bearing rocks, the kind of famous rocks, are these conglomerates. And I'm sure you did conglomerates with Trish when you did sedimentary rocks. And yeah, that's what's made famous about the Wit supergroup, is the gold-bearing conglomerates. And if we actually look, what is a conglomerate? Because I know you know this. It's a coarse-grained sedimentary rock that's composed of rounded fragments embedded in a cementing matrix or cementing material. And in these images, you can see we've got round quartz pebbles, and in the matrix, what you can see glittering is mainly pyrite, but there's gold chemically bound to the pyrite. And what has happened in the Witwatersrand supergroup is that gold has a high specific gravity. So while the gold particles are very small and wouldn't normally be, small particles you wouldn't necessarily find in a conglomerate, it's much larger particles. But the gold has a high specific gravity, so small and dense, and in this large sedimentary basin, the gold has settled out with these large conglomerates. So that's why the coarse-grained cobble conglomerates are associated with the gold. So this is a reconstruction of how we imagine this Witwatersrand supergroup looked like. So we've got our Karpvaal craton, and we've got a hinterland, we've got the granites, we've got the greenstone belts, which our craton has been rifted, and we imagine we would have shoulders of a rift and a kind of mountain land. And then in the interior we have the shallow inland sea. And what we have building up in the sea is various different layers, and these reef layers, they're called reefs, the conglomerate layers that contain the gold, and we have a number of them, and they're divided into the subgroups which make up the Witwatersrand supergroup. So we have the West Rand group and the Central group with various subgroups dividing it up. And this is basically the model for. So this is another look at the stratigraphy of the Witwatersrand supergroup, where we have, so this is a stratigraphic column, and the basement, so we start at the bottom with the oldest rocks, our law of stratigraphy, and underlying it, the oldest material are the granites and greenstone, the Archean basement, which is part of the Karpvaal craton. And then above this we have the various sedimentary units, so they're mainly shallow marine or fluvial, so a shallow inland sea or fluvial, which is deposited by rivers. And we have sandstones, and then every now and again we have these conglomerate layers, which are the reefs, which contain the gold. And we have the various subgroups. But in reality, the Witwatersrand supergroup, while our understanding is that these rocks would have formed in an originally horizontal sequence, that's not how they look today. So today, the whole basin has been tilted up, so that wherever you are on the basin, the rocks kind of tilt up a bit like the sides of a saucer. So this is a cross-section, just looking at mainly the Central Rand group, and we can see the main reef packages are all inclined. So, yes.
What does that?
Rand. Okay, well, Rand is an Afrikaans word which means ridge. So Witwatersrand means like ridge of white waters. And the gold-bearing reefs form ridges. So around Johannesburg, the various ridges like the Hospital Hill group, that forms the ridge. And because these ridges had the conglomerates which had the gold, that's why our currency is called the Rand as well. It all goes back to the history of this part of Africa. So yeah, understanding the topography, so around Johannesburg, these rocks outcrop at surface. And so gold was first discovered at surface, but the rocks don't continue at surface. The surface exposures are quite limited because the whole basin has been tilted. So a major question is, how did we get so much gold into these conglomerates? How come we've got 40% of all the gold that's ever been discovered in the world ever in one basin? So there's basically two models, and this has been a major discussion point among geologists for decades, and they disagree very fiercely with each other. So the first model is called the placer model, and this is a fluvial kind of river model, that we have a fluvial or a river source where gold has been eroded out of these distant mountains. So we have, as I said, the shallow basin on the craton with a hinterland, a distant mountains, and these are very rich in gold, so it doesn't totally answer the question of where the gold comes from. But these mountains then are eroded by massive rivers which then flow into this basin, and the gold with the high specific gravity settles out with the conglomerate layers. And we also get other heavy minerals like pyrite, which also settles out, and the pyrite is what really glitters when you look at these conglomerates, and pyrite is also called fool's gold. So this is one explanation of how we've got so much gold. And if you look at the individual little gold grains in the conglomerates, you can find rounded grains, you can find grains which have been moved by water. They've been rounded by flowing basically in a river. So that's the evidence to suggest that this is where the gold come from. But there's a second model which is called the hydrothermal model. So hydrothermal are basically just hot fluids. And this is arguing that while some of the gold is transported by the rivers, because we have good evidence for sedimentary gold, that we get a different type of gold. If you look at the actual gold grains, you get with a fine filigree texture, they just are clearly not transported by water. And the argument here is that these hydrothermal fluids, these hot underground fluids, come up and percolate through the conglomerates. And as they do this, they precipitate out basically chemical gold that's dissolved in these fluids. And so this is the hydrothermal model, that you've got gold-rich gold-rich fluids, hydrothermal fluids, which percolate up and precipitate out the gold. So while these are two kind of end member models, it's likely that the answer is somewhere in between, and that we have both, because we actually have evidence of both. We have evidence of fluvial gold that's been washed out of this hinterland, and we have evidence of hydrothermal gold that's precipitating out in these layers. So it's likely that we have both mechanisms acting that's caused such an incredible richness of gold, basically.